Welcome to the Experimental Modal Analysis Lab. I am Dr. Arnaldo Delicarri, and I'm going to show you how this beam vibrates. So let's start with a set of basics first. What is modal analysis? We have a multi-degree of freedom system like this one on the left, and modal analysis is just a change of coordinates that it's a mathematical change of coordinates that lets you transform a connected system of masses and springs into individual systems of masses and springs in a different coordinate system that then can be summed up to give you a response model. As I was saying, we have three kinds of models. So there's the spatial model, for which you usually that's usually obtained when you do your FEA, your finite element analysis. This gives you a mass matrix, a stiffness matrix, and a damping matrix. And with the analytical modal analysis, so what you do by hand or with the software on your computer, you can extract the so-called modal parameters of the structure, which are natural frequencies, loss factors, damping ratios, and mode shapes. Now, each natural frequency represents the natural frequency of vibration of a single degree of freedom system. So we have, in this case, we have three masses. So there are three corresponding natural frequencies. There are three corresponding damping ratios, and there are also three amplitudes, in this case, for these three masses that vibrate. Now, by means of superposition, starting from the modal model, you can also find the response model, which is a curve, basically, or a set of curves that tell you, these are called frequency response functions, that tell you what is the amplitude of vibration for a single of these masses. So in this case, we have a set of three curves like these. So if this is H1 for mass 1, this tells you at each frequency what is the mode of vibration, so what is the amplitude of vibration for that mass. And as you can see, this frequency response function shows three peaks, and these three peaks, it's because we have three masses. Each own mass feels as its own natural frequency. Therefore, and since they are all connected, every mass will feel all three. Now, what I have here at the bottom is the effect of superposition I was talking about. We have this mode 1. This is a single degree of freedom system vibrating, and this corresponds to the modal mass 1. This red one corresponds to the modal mass 2, and this green one to the modal mass 3. As you can see, it's very easy. By just summing the contribution of these three individual modes, these three individual masses, you'll find what happens to the physical mass. Now, these are three modal masses. These do not exist in reality. These only exist in this so-called modal space. Now, this is your physical reality. This is a mathematical reality for which these masses are uncoupled. And this is the response model that you can actually measure in real life. So what you model is a set of masses and springs. What you measure is a bunch of curves. And in between, you have the link, which is the modal model, and lets you pass from one to the other. In fact, analytical modal analysis lets you pass from a spatial model, from a physical representation of the system, to a modal model, a mathematical representation of the same system. And by means of superposition, you can also find the curves, the frequency response functions. Now, from the frequency response functions, it's possible to extract the modal parameters again. And so we do this by means of experimental modal analysis. Again, just as a recap, analytical versus experimental modal analysis. The modal model is what we want at the end, and analytical modal analysis lets you pass from physical space to modal space, whereas the experimental modal analysis lets us pass from a response model to the modal space again. So ideally, if you want to confront and compare your FE model with your real structure, you have to do this in the modal space, because there is no way, as you can see, to measure the curves and back up these matrices, which you might want to compare. So the only comparison can be done in the modal space. Okay, you'll remember these are the equations. So this is from the spatial model. So in physical space, you have, again, a set of physical masses and springs, and you can model these with their equations of motion into this simple matrix form, where you have the mass matrix and the stiffness matrix and a set of forces. Now, the modal model, instead, you use matrix algebra and the eigenvalues problem to start from the physical space, and after some manipulation, you get to this eigenvalues problem. Now, the eigenvalues of this problem, omega squared, those are the natural frequencies of your system. Now, in this case, we'll have two. You have two physical masses. Those correspond to two natural frequencies. And the eigenvectors of this problem, so this one, the first column is the first eigenvector, second column is the second eigenvector. You can bunch them into a single matrix, which is the rotation matrix or the modal matrix. And they correspond to the deformed shapes, or the mode shapes or deformed shapes of the system. Okay, so like in this case, this first vector might be 1, 1, 1, 1. That means that both masses are moving in the same direction at the same time, so going back and forth at the same rate. Whereas the second mode shape might be 1, minus 1, where these two masses move opposite to each other. So they just move in counterphase. Again, as I said, the modal model, if you take the rotation matrices, so the modal matrices, and you apply them to the mass matrix, you'll find a diagonal mass matrix. And if you apply the same thing to the stiffness matrix, you'll find a diagonal stiffness matrix. Now, this being diagonal means that what you have at the end is a system which is completely decoupled. So if you rewrite the equations of motion for the modal model, what you'll get is that each mass doesn't interact with the other mass. So what you have at the end is that modal mass 1 has got its own modal stiffness 1, modal mass 2 has got its own modal stiffness 2, and they are not connected to each other. So they live in their own space. And we already know everything about single degree of freedom systems, so this is a very, very easy to solve problem. Instead of solving a system of differential equations, we solve simple single differential equations completely uncoupled from each other. So in this case, instead of solving two differential equations in a system, two simultaneous differential equations coupled with each other, we solve a single differential equation and then a second one by themselves. Finally, as I said, you can also bunch the solutions up. You can sum them up, and you'll find that, so I say this is solution 1 of the modal model. Remember, single degree of freedom system, got a single peak, and the second modal mass vibrates with this other peak, and if you sum them all together, you'll find this is the frequency response function of your physical problem. So that's very intuitive and also very easy to visualize. Again, as a recap, spatial model, it's your own physical system. You generally get these matrices from your FE software of choice. Using analytical model analysis, you can extract frequencies, loss factors, and mode shapes, and those are the modal parameters that live in the modal space. And this uncouples your system. So this is very hard to solve. This is very easy to solve. By means of superposition, so by just summing, so the solution of this one is this red curve, the solution of this one is this blue curve. By summing the solutions, you get the frequency response function of your physical space system, and this is called the response model. Now, the response model has the nice characteristic that we can measure it directly. That the response model is just output over input. So it's how much the mass is displacing over how much force is getting applied. And so we can pass from the response model to the modal model by means of experimental model analysis. Now I want to start showing the experiment. So this is the structure we are going to study. And this structure has been instrumented with an accelerometer here. And we also have a modal hammer here. Now the accelerometer itself is a triax accelerometer. If I can show you, there are labels here. There is a label Y, there is a label Z, and there is also a label X on the side. So that means this accelerometer can record data from 3 different set of axes. Also, I can show you the cable of this accelerometer has got one end to the accelerometer, but it exits with 3 ends. So each cable, each of the 3 ends carried the signal for a single axis. And they are labeled X, Y, Z. The modal hammer itself is also it's also instrumented, so it's got a load cell at the tip. We can vary the mass of the hammer if we wanted a heavier strike or a softer strike. And we can change the tip as well, because different structures might want different tip materials. Okay, so this is a steel tip, which is very appropriate for a steel structure. Now the structure itself, it's a beam. It's been welded at some points, and it's been also marked with some nodes. So there are 19 nodes marked on this beam. So this is a way of discretizing the structure. Now, as I showed you in the slideshow, you generally have a set of masses and springs connected to each other, but in this case, this is a continuous structure. We don't have a set of masses. So we need to discretize the structure with a certain number of degrees of freedom. Now in this case, I've discretized this structure with 19 nodes. There are 5 here, 6 here, and the rest here. And I'm going to strike the structure at each of these nodes so that I can make it vibrate and observe its modes of vibration. So you might have noticed this structure has been suspended by elastic cords. Why is that? We need elastic cords because we want the structure to be free to vibrate. If this was not on elastic cord, if this was sitting on the table, what would happen is that if I strike it, the table itself is impeding some of the bending of this middle part. So that means we are not observing the full behavior of the structure. So this is called free suspension. And ideally, as long as these elastic cords vibrate at a frequency that is much smaller than the first mode of the beam, we don't have to worry about it. Okay, I'm going to show you later how we observe this kind of vibration and how we can get rid of it. Finally, we have the acquisition box. So this is the Siemens SCADA's XS. So what this does is acquire, so this has input channels. It's got 4 input channels. And we can take all the signals from the hammer and the accelerometer and feed them into the box that does basically just basic signal processing to capture the streams of data. Okay, so this that I have here is the software that we're going to use to acquire and analyze the data. The first thing that we want is to discretize and draw the structure on the software itself. Now what I have here is a list of nodes. You might notice there are X, Y, Z, and 19 nodes. So the software knows where my nodes are. and this is useful because after we've done the analysis, this is going to animate the mode shapes for us. Another thing that we might look at are the Euler angles. Now each node has its own angle, its own coordinate system, and you notice that X is the green arrow, Y is the blue arrow, Z is the red arrow. So X is green, Y is blue, and Z is red. And what you see here is that most of the points, let me show the names. So this is node 1, node 2, node 3, node 4, node 5 until node 19. So at node 19 we have the accelerometer, and we just made sure that the reference system of the structure at this node is the same as the accelerometer 1, where we have the z-axis pointing upwards, the y-axis pointing towards the camera, and the x-axis in this direction here. So this is the same. So ideally, if you look at the structure now, this is how you should be. Now this shows exactly how you see the structure right now. So node 1 on the left, node 19 on the right, with the y-axis pointing towards you. Now this tab is the tab that communicates with the actual acquisition box. So what we have here is this shows what the acquisition box can do, and we have 10 input channels. So this box is capable of acquiring 10 different streams of signals all at the same time. And in this case, we only need 3 really. And I have turned on just the first 3 channels, and I said that channel 1 is my force channel, whereas channel 2 are my 2 acceleration channels, channels 2 and 3. Okay, now I have a choice to make. I only have 3 inputs here. I've got a cable with 3 inputs, but I also have 4 outputs. I have X, Y, Z from the accelerometer, and I have the hammer that I have to capture as well. So how do I choose which 3 do I want? Well, of course, the hammer is required, so that's why I put the hammer on 1. What else is required? Let's check what kind of vibrations we want to observe of this beam. We want to definitely observe the vertical bending of the beam, but we might also want to observe the lateral bending of the beam. What we don't need to observe is the squeezing motion, so it's the axial vibration of this beam. So since the axial vibration will occur at very high frequency, imagine if I try to squeeze this is very stiff in the axial direction, and it's much softer in the bending directions. So that means I can get rid of the channel of the x-axis channel, so the longitudinal axis along the beam, because those vibrations will occur at very, very high frequency, and I don't care about those. So you generally want the lowest frequencies, because those are the most important ones that carry the largest amplitude and also are in the operational range of your structure generally. Okay, so what I am doing is the z-axis. So in channel 2, I put the z-axis of the accelerometer, and in channel 3, I put the y-axis of the accelerometer. So these are in order of importance, basically. So channel 1 is the hammer, it's probably one of the most important ones. Channel 2 is the vertical bending, that's what we want the most. And channel 3, as a bonus, we would also like to see the vertical bendings of these beams, the lateral bendings of these beams. What you have here is the sensitivity. Now, how does this box here, this acquisition box, doesn't understand anything about units. It doesn't understand newtons, it doesn't understand meters per second squared. What it does understand is voltage. It's a circuit, it's a circuit board, so all it understands is voltage and current. So the idea is that when I strike the beam, the load cell has got a piezoelectric crystal inside. That means it transforms deformation of the tip into electrical charge. This electrical charge must then be amplified by this box, and it can be measured, so it can be recorded in the stage. But what you record is a difference in voltage. It's a voltage drop. And that voltage drop must correspond to a certain amount of newtons. Now this you know by means of calibration. Every instrument comes with a set of data sheets or data cards, and on these data cards you'll find the sensitivity of the instrument. Now I can read here that these are the calibration data card for the accelerometer. So for the z-axis of the accelerometer, so channel 2, I have 102.7 millivolts per G of sensitivity. That means every time the acquisition box reads 102.7 millivolts, that means 1 G. So if it measures twice as much, it's 2 G. Okay, so that the box doesn't need to know this, but if you feed this information to the software can make the conversion for you. So instead of showing you the voltages, it shows you directly the engineering units, so G and newtons in this case. Now the data card of the hammer shows that it's got 2.234 millivolts per newton. The z-axis of the accelerometer is 102.7 millivolts per G, and the y-axis of the accelerometer is 98 millivolts per G. Now these are nominally, these instruments are sold with nominal sensitivity of 100 millivolts per G. Of course, so what you buy on the website is 100 millivolts per G accelerometers, but of course you will never get exactly 100 millivolts per G accelerometers. Every accelerometer and every channel of the accelerometer has got its own sensitivity, so make sure you understand what you're doing and what you're buying as well. These need calibration, so these sensors need every 3 years, every 5 years, or every year, depending on how critical is your industry. They need periodic recalibration. So that means that after a set of 3 years or after a set of 5 years, you might want to return these instruments to the company that recalibrates them, and then it ships it back to you for a hefty fee. What you can do is also recalibrate these yourself. So say this software here has got a calibration tab. So if you don't trust, so if it's past too much time from since your last calibration, you might want to recalibrate your accelerometers. What you need is a known source of acceleration, so that you can compare your accelerometer with your known source. Of course, this also means that you take full responsibility of your measurements, because every time you recalibrate something, you must also sign a certificate of a calibration certificate that says, okay, this is now the sensitivity of this channel of this accelerometer is now this much. And that's under your own responsibility, also legal responsibility. Okay, now what I'm going to do is to set up, to check if the instruments are all working. So I have a scope here. Each one of these windows is a channel. So the first window here is the hammer. You see newtons and seconds. The second window is the z-axis of the accelerometer. The third one is the y-axis of the accelerometer. Now I'm going to start recording something just to make sure that everything is working correctly, but first I need to set up some settings. Now what I want is the bandwidth first. Now the bandwidth is how much of the spectrum I want to capture. So we are interested in natural frequencies from 0 to 2000 Hertz, ideally. Okay, now for this structure here, I know because that's where the most important frequencies fall. Now, if you have a different structure, you might want to have an idea on what is the operational range of that structure, or if you have an FE model, you can also see the frequency response functions. You can simulate the frequency response functions. Those will be approximated, of course, but you'll have an idea on which range to capture, so which range you are interested in. I don't have 2000 Hertz. I can only choose 2048. I can choose 1024. That's because in order to have a spectral information, we need an algorithm that is called fast Fourier transform. And that fast Fourier transform, that fast in the algorithm, it's only fast if you're using power of 2, if you're using a range that is a power of 2. Okay, so 2048, 1024, so the next step up would be 4096. What we need is resolution. Remember, the frequency response function is a curve that has peaks. What we want is a fine resolution, because if your resolution is too low, you might miss the peak. Okay, so we must make sure that we capture a good enough resolution. Now, in this case, I've chosen 0.25 Hertz, so it's 1/4 of an Hertz of resolution. That means that over 2048 Hertz, that's a lot of points that we are calculating. But that also sets an acquisition time. So the fast Fourier transform relies on the length. So if you want more resolution, you have to capture signals for longer. So the longer you capture your signal, the finer will be your final resolution of the frequency response function. Now, for this set of bandwidth and resolution, we got 8,192 points, and this corresponds to an acquisition time of 4 seconds. That means that after every impact, I have to wait for 4 seconds before I strike again, at least. This makes the test a bit slower, and this will become even slower because, of course, one strike is not enough. We want to take averages. So for every point, we're going to have 3 to 5 averages. Ideally, you want 20 averages. Okay, now for the sake of this test, in order to keep it short, I'm just going to use 3 averages per point. Okay, let's start. And I set a trigger here. A trigger says that when this channel 1 of the hammer, reaches 5 newtons, then you can start recording. Because otherwise we'll be continuously recording, and I must sync up my strikes every 4 seconds. That's impossible for a human being. So what we do is ask the software to not record anything unless there is a ramp up from 0 to 5 newtons of this hammer. And when it ramps up, I also set a pre-trigger level, so that the box is continuously recording, and after it feels the trigger, it goes back and records everything from minus 5 milliseconds. No, it's half of a tenth of a second. Okay, so this is my first strike that I've done earlier. So let's do one strike. So after 4 seconds, you see the picture gets refreshed, and what you see here is the hammer has got a spike. It's a very tiny spike, and the accelerometer, as you can imagine, is a decaying set of exponentially decaying sine waves. It doesn't look like it, but if I zoom in, you can see it's a sine wave that it's decaying. Okay, it's not one sine wave, of course, it's many sine waves, because that's a complex structure. It's not a single degree of freedom. And you got 1 for the z-axis and 1 for the y-axis as well. Of course, if I strike from the side, striking from the side means the y-axis is more excited than the z-axis, of course. Now what you have here, these colored bars, these ones are the ranges. Now this is a set of, so I told you what we need is amplification. So this box is capable of recording with a resolution of 24 bits. That means you have two to the power of 24 levels at which your signal can live. Now this means that if your signal is too large, like this one, you'll get red bars. See, these red bars means that your signal has clipped. So it's gone outside the possible range of capture. And this is bad because if ideally the Fourier transform of a sine wave is a sharp line, but if you have a clipped sine wave, that's a shallow line that has leaked over the entire spectrum, and that's almost useless to you. So that's a very large error that you make over the entire range of frequencies. So what you want is your signal must not clip, so you must have a level of amplification that gets you to the largest possible value without clipping. And so you might be asking, why don't you just have a low level of amplification? Well, if you have a low level of amplification, something else happens, and it's called a loss, and it's a loss of resolution. It's called, you see some chunky, okay, I lost it, I'm sorry. So I wanted to show something on the whiteboard right now. Okay, so what I was saying is that for the FFT of a sine wave looks like this, very sharp, but if you have an FFT of a clipped sine wave, so something that goes out of bounds, you'll see something like this. Okay, so this has a very large error over every other frequency, so that's this thing, so this out of range, this overloading of the channel you want to avoid. But again, on the other end, you want to also to avoid to be too small, because what happens if you have a range that is too small? That means out of the 2 to the power of 24 levels, you might only be using 3 levels, or in this case 7 levels. If you use 7 out of these many, what you have is that your signal will look like a set of steps. So this is a blocky signal that you have. So your sine wave, your analog sine wave will be captured digitally with this horrible set of steps. And if you do the FFT of this, you'll get something bad as well. So you want to avoid being too low in your range, and you want to avoid being too high on your range, so you have to set a level of ranges, so a level of amplification of the box for every channel. So every channel has its own sets of amplification, and you want to be set it so it's about 80%, 90% of the full range. That's the ideal range. Okay, so as I was saying, these red bars mean that we are overloaded. We have overloaded the channels. So let's see how much we have to strike in order to be in the green range, which is the, I told you, 80%, 90% of the full range. Okay, orange is still good, means that we are above 90% of range. So that means a medium to a soft impact is enough to capture everything. So I'm waiting, every time I'm waiting 4 seconds, because that's the acquisition time. See, that's 4 seconds here, so every time I strike, I have to wait for at least 4 seconds for this. Okay, one thing you might want to avoid when you strike is, well, you must make sure you have a technique of striking, because you want to avoid double impacts, something like this. You want to avoid this, so you can hear it if you have a double impact. And this, as you can imagine, you can also see it in the pictures. So this is a double impact. And of course, you tell me that's if you do the fast Fourier transform of this, you also get very large errors everywhere in the spectrum. So you must be very careful to capture a single decaying set of sine waves and a single spike in the hammer. So ideally, the technique would be to have this ready and to grab the hammer from its own center of gravity, so say around here, so you can easily remove it as soon as you strike. Yeah, something like this. Now everything is set up, everything is working correctly. Let's go to the measurement setup. We just want to make sure that the trigger is working. So see, in this case, the trigger might be too low because by just moving the hammer, I'm triggering it. Okay, that's bad. Of course, the hammer, I told you inside the hammer there's a mass, and if I shake it too hard, that mass is triggering. So what I want to do is ask the software to help me. So I will strike a few times and the software will tell me exactly what's the level of trigger that is required. Just make sure that I don't go in overload. Now these are the suggestions from the software. Let's verify that the trigger is working now. So if I shake it, oh, it's still, yes, okay. So let's do it again. Yeah. Now just by shaking it, it doesn't trigger, but if I strike it does. With a low strike, so soft. Okay. So if I strike too hard, of course, I get overloaded. Let me check the bandwidth as well. Okay, so this is what you see. On the left-hand side, you get the fast Fourier transform of the hammer. Now the hammer is a single spike. Ideally, mathematically, if it's a single spike, a perfect spike, you should get a constant line. So you get a constant line that doesn't drop. Now, of course, this is not a perfect strike. So a perfect strike, a real strike, always feels a drop towards the end of toward the higher end of the spectrum. This one is the FFT of the accelerometer. Now this is the X, this is the Y-axis. Let's change this to the Z-axis. So this is the Z-axis of the accelerometer. As you can see, it's got peaks. And now the frequency response function So the response model that we can measure is just this curve divided by this curve. Now, if this is constant, of course, this is the same, it retains the same shape. Ideally, this should be completely constant. So what we can say is that we can't really trust this last part of the spectrum, because the hammer can't reach that far. Okay, now if you have a bad impact, like a double impact, if you have a double impact, you see what happens. It's very bad. So this drops a lot, and also it's a shaky signal. So it's not a continuous line. So let's give it another run. So this is a soft impact. Very good. This is an impact close to the accelerometer. I'll zoom out this one. Okay, so see, it's quite good impact and quite good accelerometer, FFT. Now the next step is we want to make sure that windows are applied. What are windows? Windows are just multiplication functions to the signals we are using. Since we want the hammer to be perfect spike, so that it doesn't ring or it doesn't do anything after the spike, and we also want ideally the accelerometer, the decaying of the accelerometer, to reach 0 at the end of the 4 seconds, and this might not happen, because after 4 seconds, even after 4 seconds, this is still vibrating. And again, if you don't capture the entire decaying part, if you do the FFT of that, you get errors. So we can force it to 0 at the end, and we can also force the hammer to not record anything after the spike. So how we do that? Well, first we measure a few times. And now, as you can see, I can apply a window, so a force exponential window to the hammer. So the left hand side is the hammer. This is before and this is after windowing, and this is the result. It's quite nice. And again, this is the result before and after windowing of the accelerometer. Now what you have, and let me put this in Z, what you have is we are multiplying this signal times a decaying exponential that reaches 0 exactly at 4 seconds. This means we are adding something like an artificial damping. So we are artificially damping the structure mathematically. Now this might seem like a problem, but since we know how much damping we are adding, at the end, when we do the analysis, we can also remove that damping if we know how much we have added in pre-processing. In post-processing, we can remove that much damping from the results. Okay, this looks nice. Now, The last thing is to test the driving point. The driving point is a very important point of the structure. It is the point where we are measuring. So point 19, if I strike on point 19, the accelerometer is recording what happens if we strike where we measure. This is a very important point because it lets us scale properly the mode shapes. Now, of course, this beam might bend, and you know that eigenvectors, so the mode shapes of that beam, are the same up to a scale factor, so it doesn't matter if it bends by 1, or it bends twice as much, or it bends 3 times as much, or it bends the other way, -1, -2, -3. That's the same mode of vibration. But for a certain Newton level, so for a certain amount of newtons, for a certain level of force, you will have a certain amount of deflection. So the driving point gives us the baseline that says, okay, if I impact with 1 Newton, I get this much acceleration out of it. If I impact with twice as much, I get twice as much. So what we are doing here is to strike the driving point from the bottom. Let's see if I can do it from the bottom. No, probably not. So I will strike the driving point very close. Ideally, I should strike the accelerometer itself, but of course, if I strike the accelerometer, I won't get anything from its recording. So what I want is to strike very close to the accelerometer. Okay. As I was saying, we want to record first the driving point, because the driving point will let us scale the mode shapes properly. So we'll start with 5 averages. So it's 5 averages. Implicit accept means if anything goes well, it will automatically go to the next average, so I don't have to click go every time. And if it goes in overload, it will not record what I have been doing. So I will strike point 19, which is where the accelerometer sits. Of course, I will not be striking the accelerometer itself. So let's do this for 5 times. Okay. 1, 2, 3, 4, and 5. Okay. Now this, as you can see, gives us, this is the frequency response function. You can see it from the units. That's G over Newton. That's output over input. So this is, let's say, at At 26 Hertz, I have about data. I have about 10, 20, 40 G of acceleration. Now that I'm done with my So now that I'm done with my driving points, I'll go back to point 1 and I will start recording all points. I will use 3 averages just to keep it short. Ideally you want 10 to 20 averages depending on how large is your structure, how critical is your component as well. So I'll start from point 1. This is going to take a while. And I have to wait 4 seconds between each strike. I will always keep an eye on these levels, on these ranges, and I will always keep an eye on what's going on in my hammer and frequency response. For what you have here is on the left hand side you have the instantaneous frequency response function, so that relates to my last strike. This one is the average of the 3. Now, of course, these look exactly the same right now because I've only done 1 strike, but with my second strike now, this left-hand one is my second strike, and this is the average of the last 2 strikes. Again, okay. Now this is the last one, and this is the average of the 3. Of course, since these were 3 good impacts, I got a good average as well. And what you have here, and in this last plot, is something that is called coherence. Now, coherence is an index. As you can see, it goes from 0 to 1. In this case, 0.446, but it goes from 0 to 1, and it represents how much of the output has been caused by the input. So it says if I have captured the entire cause of the output as an input. Ideally, we can make this drop to, say, half as much if I had some music playing around, very loud music. So that music, say if I have speakers here, that music will excite the structure, of course, because sound is just vibration of the air. So if molecules of air are vibrating alongside so the speakers are making the air vibrate, so the air it's making other air vibrate, and at some point the air surrounding the structure will vibrate. That means the structure will vibrate as well. So this thing I'm not capturing, I'm not recording these. I'm only recording my strikes. So if I do both at the same time, the accelerometer will pick up the vibration of both the hammer and the music, whereas the signal box, the acquisition box, will only capture the hammer. So the coherence will be low because not everything that we captured from the accelerometer came 100% from the hammer. Okay, so that means, so coherence of 1, and see here I have a nice 1 almost for the entire range. So starting here, this is, I have a drop in coherence at around 1600 Hertz. But that's fine, that's very high in range, and also it's almost a single point. So it doesn't matter, everything is fine. Sometimes you have a drop in coherence at 50 Hertz, and that's due, no, not in this case because it's where is it? No, 50 Hertz. Now, not in this case because everything is well shielded, but you know that your mains power is running at 50 Hertz. So if anything is interfering with the accelerometer, so if the cables are not shielded properly, you might have this other output, so this electrical frequency that is coming in and it's messing up with your coherence at 50 Hertz only, because that's only a single frequency. Okay, now the software is asking for number 2. Let me see if I can do the auto increment. So let's do number 2. So I will be striking point 2 now 3 times. Okay. Now, as you can notice, the coherence looks horrible. So it looks horrible right now because the coherence is based on averages. Now, of course, this is one strike. You can't have an average of one strike, so the coherence looks horrible. So as soon as we have the second strike, the coherence will start making sense. And there you go. So the coherence looks good. We still have that drop. That drop is not a lot though, because this lower bound is 76%. So this is not a dramatic drop. Okay, that looks much nicer. And now we are already being asked from the software to measure 0.3. What you can show here as well is have a visual aid. Now in this case it's easy, but ideally you want a visual aid to tell where you are supposed to strike. Since we gave the software geometric information, the software is telling us please strike this point here, which is node 3. Now of course for a beam it's very easy to keep track of these, but if you have a larger or more complex structure like a curved structure or an airplane or a car frame, anything else, it might be useful to have this geometric feedback. So even if you take a break in between strikes, you know exactly where you want to strike next. So 0.3, this one. Okay, it's not too bad, 0.01. Okay, so since I don't like this free ranging of the y-axis here, I will just change this to, I want this to go from 0 to 1, because I know the coherence goes from 0 to 1. So as you can see, this looks much nicer now. We're looking at 0.4. Oop. Probably too soft. Still captured everything. So as you can see, the ranges are on the black side. So you want to be on the green side, but it's still fine. Nice. As you can notice, we have some peaks. We have larger peaks and smaller ones. Now these smaller peaks might be due to the lateral bending, okay, so the torsional mode shapes. That's because if I strike exactly on the midline of the beam, I don't excite any torsion, but if I strike a bit on the side, I might excite a bit of torsion as well. And that might be captured here in these very, very tiny peaks. Look, this one here is tiny as well. We're looking at 0.5. So 0.5 is very close to the welding. So I'll try to be careful. See, close to the welding, it doesn't look nice. Looks a bit wobbly, but that's what we have. Okay, so it's still good enough. You can still see the peaks. It doesn't look too noisy. 0.6, again, this is close to the other welding. Okay. Okay, well, I've seen better, but it'll do. 0.7. See, it's very reliable. You always get the same shape, more or less. 0.8. I'm always keeping an eye on these bars, but also how it looks. So this is the time history of the hammer and accelerometer. This is the FFT, no, this is the power spectral density of the hammer and accelerometer. We are doing 0.8 and we are doing average number 2. So strike 0.8 again. Okay, that's good. 0.9. Point 10. Point 11, close to the welding. It's good. Point 12. Now you might notice how much time it's taking for just this very simple experiment, and that's because we're only taking 3 averages. Ideally you should be taking many more, and also this is only 4 seconds of acquisition. Sometimes you also go through 12 seconds to 20 seconds of acquisition. So that means that every strike would be 20 seconds and every average will take 20 seconds. So your test, that's why it's called a field test day. You take a full day generally to go through a single test. We're doing 0.12 last average, last strike for the average. And then 0.13. Now as I move closer and closer to the accelerometer, I'm making my strikes a bit softer because I don't want to overload the accelerometer channel. When I was here at 0.1, I could strike harder because the energy would get transmitted along the beam and we'll lose some of the energy along the beam. But if I strike too close to the hammer, to the accelerometer, I want to strike softer, of course. Again, 0.13, strike 2. And strike 3. Point 14. Point 15. Now, if you make a mistake, now I'm going to make a deliberate mistake, say a double impact. Of course, your average will get screwed. Okay, so this is horrible now. But luckily, we can reject our last impact so that your test is not wasted. So still doing 15. Number 2, again. And number 3. Now this is all thanks to the software, because ideally if you didn't have a software, you will have to accept it and redo point 15 from scratch. Point 16. Okay, all looks nice. Another thing I wanted to show you is that these frequency response function, as you can see, you have amplitude and phase. So this is a complex number. So frequency response functions are complex numbers. So every frequency is associated with a complex number. So you either have real and imaginary part, or you have amplitude and phase. Now in this case it's amplitude and phase, but if you want, you can also change this to be real and imaginary. So this is the real part, and this at the bottom is the imaginary part, so real and imaginary, or you can choose the amplitude and phase. Now this is the amplitude, linear amplitude. What you want is probably the log amplitude, because linear amplitude gives you linear amplitude. You see the largest peaks, but you can't discriminate between the smallest ones. Now the smaller peaks are still peaks. Even if they are at low amplitude, they still have natural frequencies. So you can't, you need a way to discriminate between those, and the best tool is to plot them in log shape. So you see here, these peaks here, they are there, but in the amplitude, in the linear amplitude, you can't see them. We're looking at point 17. Now this one is very close to the suspension, so I'll try to be careful. 1, 2, and 3. And then 18. And that's it, because 19 we did it with the driving point. Now, and I go on to the validation tab. Now the validation tab shows you all the frequency response function that we captured, all of them. You can look at them one by one to see if anyone is noisy or if anyone has issues. Now this one looks noisy, but that's because this is the part where we had the low coherence, remember? And it doesn't matter, it's not a peak, it's on a, it's called anti-resonance. So that's fine. Of course, these very low ones will always be noisy, because if you think about it, this is G over Newton. So this is force, is acceleration over force. And if you have a very, very, very low acceleration, that's almost 0. Okay, so you won't have, the coherence will give you output over input, but the output is almost 0, whereas the input is a good number, so the coherence doesn't know what to do. It's not very accurate in that sense. Okay, scrolling through, the frequency response functions they all look very nice. So this is the y-axis. So these are the lateral peaks that you see. So you see, well, in the frequency response function you see all the peaks. Now the highest ones in this case are the y ones, because you're looking at the y direction, and these ones are the z ones. So as you can see, this peak here shows in both z and y. Of course, in the z direction it looks tiny, because we're looking just at this vertical one, and in the y direction it looks larger. So these are all very nice, and we have, I'd say we have 4 main peaks. So 1, 2, 3, 4 in the z direction. So we have four modes of vibration in the vertical around the frontal axis. Okay, now that everything looks fine, so these are all the z ones. And these are all the y ones. Now, the only thing that is left to do is to take all these frequency response functions, one per point, well, it's 2 per point, one in the z direction, one in the y direction. So we have 38 of these, and we want to extract the frequencies and the mode shapes of this structure. So I'm going to change software now. Let me save first. I will open the modal analysis section of the software. I will open Okay, so now we have to follow these tabs, and we have to select which frequency response functions we want to input in our algorithm that does the extraction. Now the algorithms are many. There are many algorithms that do this analysis. Now the simplest ones are called peak picking. So you can select every single peak and it does the analysis as if it was a single degree of freedom system. Now this is not very accurate, although it gives you a very good indication of the frequencies at least and the damping factors. So what I have here is the green one is the selected frequency response function. I can change them. I can select a different point. The red one, the red curve, which doesn't change, is the sum of all these frequency response functions. Now, it doesn't mean anything in physical terms. It doesn't mean anything to sum all the curves all together. But what happens is that looking at the sum, you see the peaks more clearly, because all the peaks will be summed up. And that means you will see very clearly where are these peaks. So if I take just one frequency response function, you see here, this peak is very small. But in the sum, it looks very large, because it's summing all of these for all 38 curves. So this red curve gives you an indication on how many peaks you want to choose for your analysis. So I'll select all of them, and I will go through the algorithm. Now this algorithm is the proprietary algorithm of Siemens that's called Polymax. Again, you have many different algorithms. This Polymax one is one of the best ones for this analysis. And look at this. What you see here at the left end of the spectrum, let me zoom in. So if I zoom in at the left end, you see a peak. What's this peak? Well, this peak here happens at 4.4 Hertz. This peak is this. So this is the rigid vibration of the structure at the elastic chords. So these elastic chords are vibrating at 4 Hertz. So 4 times a second, this structure goes up and down 4 times a second. And that's why I was saying earlier that it doesn't matter if it's not a perfect free condition, so it's not suspended in mid-air. Doesn't matter if it's not perfect as long as these elastic bands have a frequency that is very, very small and it's well away from the first peak. Now this is our first peak happens at 235 Hertz, more or less, and these peaks are at 4 Hertz, so that's a large, that's a very good separation. So we can just get rid of them. So we don't check, we don't take anything before this 193 Hertz, and I want to analyze everything up to 12,000 Hertz. So the algorithm will just take care of everything that is in between 193 and 2000 Hertz. Another way of looking at these is imaginary sum. So if you want to have a look at your peaks, so this green curve is the sum of the imaginary parts of the FRFs. Now this also gives you a clear indication of where all the peaks, where the important peaks are. So let's use sum and imaginary sum for this. So this is the algorithm that it's working right now. Let's have a order of 50. And as you see here, you have a column, you have columns of symbols. Now every symbol means something. Now O means that the peak was newly found. V means it's stable in frequency but not frequency and shapes but not dumping, and so on and so forth. So S means that the peak is stable. What does it mean for a peak to be stable? It means that at every order, if you look at the right hand side here, I have numbers. So these numbers mean I'm asking my algorithm, in this case, to fit 7 peaks in this curve. So can you find 7 peaks? Yes, and it tells you this, and that. Then it says, then I ask him, can you find 8 peaks? And he tries to fit 8 peaks. Then I ask 24 peaks, and then I ask 37 peaks. And if all the peaks I found over the orders, it's all the same, that means that the peak is stable. Now if this was noisy, a noise can have a peak. You know, if it's noisy, it might look like a peak. But over the orders, it will not find always the same peak, so it will be unstable. So ideally what we want is to just pick all the stable poles, like this one, this one, this one. So this one, see, it's too windy. So this doesn't look like it's a stable thing. In fact, there is no peak here. So it looks like it's just noise. It's picking up noise. So I will not select this one. I will select this for extraction. Here it looks like I have 2. But this right one, I don't see it. So I'll just pick this left one, and I'll pick this one. This one also looks like a noise. So it's not very stable. This one, no, this one, and this one. I have selected 7 modes. 7 modes, and I also have, for each mode, I have its frequency, 260 Hz is my first mode, and 0.27% is my damping ratio. Now the damping ratio has already been stripped from the added artificial damping we added earlier. Okay, now that we have selected these, I go on to calculate the mode shapes. So this is mode shape 1. As you can see, it looks quite nice. Let me see. No. Okay. So this is my first vibration. As you can see, there are nodes. I'm going to show you what are the nodes. Now these gray ones are the undeformed nodes of the structure. These red ones are, of course, the deformed shape that's also vibrating of the structure. As you can see, this point, which is node 5, this one here, for at 263 Hertz, 260 Hertz, this node 5 is not moving. That is called a node of vibration for that structure and that frequency. So at that frequency, this point is not moving. Also, there is a point in between. Let me show the names as well. So in between node 14 and 15, so around here, for mode 1, this structure is not moving. Now you don't need the animation because this is the mode shape. Remember I told you the mode shape is a vector of numbers? Well, each number corresponds to an amplitude. So this vector is 19 numbers long, and each number is how much the corresponding node has displaced. So number 1 is how much node 1 has displaced, node 2 is how much node 2 has displaced, and so on and so forth. So see, for node 5 we almost have 0 as amplitude of displacement, and these ones as well. So let's animate back. Mode 2 is this one. It doesn't look like much probably because it's a lateral. What? I'm not sure what's going on. We have a visualization issue. Probably. I'm not sure what's going on. Go back and go back. No. Okay, mode 2, mode 3. Now this one is a proper vertical bending as well. It's mode 4, mode 5, mode 6, and mode 7. Now these ones look a bit more like lateral ones. So what I want to do is repeat the analysis without including the lateral bending, because I'm only interested into seeing the vertical bending. So let's go back to the selection of modal data. I will exclude the lateral frequency response functions, and I'll go through the analysis again. Oop. Now in this case, I'm taking these 5. This one, this one, this one, this one, and this one. And so only accounting for these 5, I find mode 1, which again I don't know why it's looking so horrible. Okay. Mode 1, mode 2, mode 3, mode 4, and mode 5. Now, as you can see, mode 4 has more to do with this part of the beam, so it's like of a local mode rather than a global mode. So it's because it interests just a part of the structure rather than the entire structure. This is usually the case when you have asymmetric structures. Some parts will start vibrating first, and then higher in the spectrum of frequencies you'll find the other part is vibrating. Like I would say that the global modes are just this one, this one, this one, and this one. Also, another thing I want to show you is that for the lowest shape, you have 2 nodes, one here and one here in between these 2. And for higher modes, you have even more. So you have one here, then you have one here, and you have one here. Okay, so for mode 2, you have one more node. For mode 3, of course, you also get one more node. 1, 2, 3, 4. And for mode 5, which is the other global mode, you have even more nodes. That is the case because the natural frequencies are associated to the mode shapes. So the lowest natural frequencies correspond to the simplest mode shapes. So as you go up in frequency, the mode shapes become more and more complex. Complex, not mathematically complex in the means of geometrically complex, because these are all complex numbers. Anyway. Now the very last thing is we want to validate our results. Validation, we do it by means of, if you recall the slides I've shown you, you can, once you have your modal analysis, you have your mode shapes, natural frequencies, and loss factors, you can do superposition of these to find the frequency response functions again. Now these frequency response functions that you find by superposition, you can compare with the ones that you have recorded from the actual data and see if your extraction was correct. Now we are comparing the frequency response function 1 of node 1, that's in red, with the one that we have synthesized from the extracted nodes. So you see in the red curve we have this tiny peak and these tiny peaks here. In the green one we only have the 4 main ones, because that's what we picked out of everything. And as you can see, this has a correlation coefficient of 99% with an error of 0.1%. And so we can have a look at all of them. So 99%, 99, 99, 99, they all look very nice. Of course, we didn't pick anything because these were lateral peaks. I told you we weren't interested in lateral peaks. So our synthesis in green doesn't show any lateral peak. And of course, this here also shows a greater error, but this error here is very small because we are in log scale. We are very low in log scale, so this is tiny. This is a tiny difference. Although it looks large only because we are in log scale. In fact, if I switch this to linear scale, it looks like there isn't even a peak there. It's so small, doesn't show. So the 3 ones, the first 3 are the most important ones, really. Okay, so as you can see, all of them are quite nice, and this is the driving point that we captured. Now the last validation trick, remember the properties of eigenvectors is that they are orthogonal to each other. Orthogonal to each other means that if you take the projection of one vector of one eigenvector onto any other eigenvector, you get 0. Now what does it mean for mode shapes to be orthogonal? How can a shape be orthogonal to another shape? Well, orthogonal in this sense means it doesn't look like the other shape. So any shape, any mode shape doesn't look like any other shape. And I can show you this by creating what we call automac matrix. Now this is a matrix, this one here is a matrix that compares mode 1 with mode 1, mode 1 with mode 2, mode 1 with mode 3, mode 1 with 4, 1 with 5, and then 2 with 1, 2 with 2, 2 with 3, and so on and so forth. So you can fill the table, and the comparison is made by projecting one eigenvector onto all the other eigenvectors. I told you, ideally, the projection of one with any other eigenvector will be 0. And here we get 100% 1 and 1. Of course, 1 looks like 1 100% of the times. 1 and 2 we have 0.89%, so it's almost 1%, so that's correct, all considered. This mode 1 and 3 look 7% like each other, still good. Mode 4 looks 35% like mode 1, and that's because mode 4 is a local mode. So it's a local mode. This is mode 4. As you can see, this part of the structure is more interested, whereas mode 1 is global. And this is mode 5. We get 2%. Now I can show you this better if I use a matrix. So you can see mode 1, and of course on the diagonal of this matrix we have all 100%. That's because we have mode 1 with mode 1, mode 2 with mode 2, 3 and 3, 4 and 4, 5 and 5, of course those are all 100%. But off diagonal I'm expecting all these ones to be 0. And these are almost 0, barred from mode 4, because mode 4 is a local mode, so it resembles a bit all the global ones in a non-trivial way. So ideally what I will do now is to go back to my analysis. Since I don't like it, I will go back to my analysis and I will unpick mode 4, because I'm only interested in the global behavior of this beam. And I will recalculate the shapes. I now have only 4 modes. Now mode 5 has become mode 4 because we got rid of mode 4 earlier. And I can resynthesize everything. Of course I have a larger error now because I'm not considering this one anymore. This one that I considered earlier now is not considered in this new set of things. But in validation, if I recalculate the matrix, I now have all zeros everywhere but on the main diagonal. Okay, this ends the experimental model analysis lab. I hope you enjoyed it. I know I did. Thank you very much.